first trend has to do with the atomic radius. So here we have in teaching model number 1 a diagram which shows how the atomic radius changes in going from one element to the next. I provide you both the numbers corresponding to the radius in picometers, so I'll just put down that you have to keep in mind that the units for each of these numbers is picometers, in other words 10 to the minus 12 meters. Also, I show you diagrammatically the size of each of the elements so that you can be comparing them. Now, as you might expect, the atomic radius is an estimation of the size of the atom as determined by the position of the valence electrons. The outer edge of an atom is where the valence electrons are. Of course, this is kind of weird because, of course, the valence electrons are waves, and they can't be located with any degree of certainty. You can only talk about the probability of finding the electron. Yet remarkably, an atom behaves something like a billiard ball, something like a sphere. So we can think of each of these atoms as being spheres with a certain radius. Now, how the radius is determined depends on the nature of the element and the technique. One way to picture this is if you have a pair of atoms together, the radius will be half the distance between the nuclei of these two atoms. This can be determined by techniques like X-ray crystallography. However, the exact measurement may differ depending on who did the measurements, the technique they use, and so I would not pay too much attention to the exact numbers here. And of course, we would never ask you for the exact numbers of the atomic radius, but rather you need to know more or less the trend across the periodic table and down the periodic table. Now, just looking at the diagram, it should be pretty obvious what these trends are. Across the periodic table, I think you can see that the size or the atomic radius of the atom decreases. And so I'll just summarize it here. Down the periodic table, hopefully you can see that the size of the atom or the atomic radius increases. Now again, this doesn't apply in all situations. So for instance, when you compare aluminum to gallium, you see that in fact the size goes down. These anomalies are difficult to explain and again may be tied to how these measurements are being made. I'd like you to be aware of the general trend. So one of the things that we can ask you is to simply state what is the trend of that particular property. So again, across the periodic table, the atomic radius goes down. Down the periodic table, the atomic radius goes up. Now, as we have 4 different trends that we'd like you to know, it would be perhaps difficult and confusing just to memorize the trends. So rather, I'd like you to understand why we think these trends happen. And again, these trends are related to the electronic structure of the atoms in each of these cases. So let's work on developing an explanation. In this activity, I'm trying to provide you with a scaffold to develop an explanation when you answer a question, for instance, on an assignment or a quiz or a test. And I hope that you'll think of the scaffold when you answer such a questions and be able to develop a beautifully constructed, well thought out answer. So here we go. As I stated before, across the periodic table, the most important thing is the fact that the nuclear charge changes. And what does the nuclear charge do? Well, it increases. And so if I ask you to explain a trend across the periodic table, that should be your first statement. The nuclear charge across the periodic table increases. Period. That's all you need to say. Well, what is the outcome of the nuclear charge increasing across the periodic table as a result of more protons in the nucleus? Well, the valence electrons, which determine the size of the atom, will be more attracted to this greater nuclear charge. So the force of attraction between the valence electrons and the nucleus would increase. If the attraction has increased, well, those valence electrons will be pulled closer to the nucleus. And indeed, that's what we're seeing across the periodic table. And so the radius will, of course, decrease. So you can put this together in one complete sentence or a small paragraph. Across the periodic table, the nuclear charge would increase. This will result in the force of attraction between the valence electrons and the nucleus to increase. As a result, the valence electrons are pulled closer to the nucleus. Therefore, the atomic radius decreases. That's the kind of explanation that we're looking for. Now, down the periodic table, I use the example of helium, but note that we can look at any of the columns. Of course, the most important thing is that the valence electrons are further from the nucleus. And well, if it's the valence electrons that determine the size of the atom, well, therefore the valence electrons are further from the nucleus and the atomic radius will increase. These are the kind of explanations that we're looking for. You can see that we're making use of the electronic structure and the position of the valence electrons to be able to explain these trends. Now that we've been through this once, you'll see that it is essentially the same process to explain the other trends that we'll be looking at.